The night of September 7th, 1940, Flight Lieutenant Harold Balfour sat in the cramped cockpit of his Avro Anson, circling at 8,000 feet over Kent. His hands gripped a device that looked like it belonged in a physics laboratory, not a military aircraft. 2 crude oscilloscope dials, a tangle of wires, and a receiver cobbled together from salvaged radio parts. He was hunting something the Germans believed was invisible, a radio beam. And on this night, he would prove that the Luftwaffe's most sophisticated navigational technology, the system that was supposed to guarantee the destruction of London, could be turned against them with nothing more than clever physics and audacious deception. This was the secret electronic war within the war. While Spitfires and Hurricanes fought in daylight skies, a different battle raged in the electromagnetic spectrum. The Germans had developed Knickerbein, a revolutionary radio beam system that allowed their bombers to navigate with precision through the darkest nights, through clouds, through conditions that made visual navigation impossible. They believed this technology was undetectable, unjammable, and would deliver German bombs onto British cities with mathematical certainty. They were catastrophically wrong. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The story begins not with pilots or bombers, but with a prisoner of war and a chance conversation that would change the course of the Blitz. In May of 1940, just weeks after the fall of France, a captured German bomber pilot named Oberleutnant Hermann Schmidt sat in an interrogation room at the Combined Services Detailed Interrogation Centre outside London. He was cocky, certain that Germany's technological superiority guaranteed victory. The British interrogator, Squadron Leader Reginald Jones, was only 28 years old, a scientific intelligence officer who had been pulled from his physics research to join the intelligence service. He had been asking routine questions about German bombing accuracy when Schmidt made an offhand comment that would unlock everything. "Your blackout will mean nothing," Schmidt said, lighting a cigarette with the confidence of a man who believed the war was already won. "We do not need to see your cities to destroy them. We have methods you cannot imagine." Jones pressed carefully. "Methods?" "Knickerbein," Schmidt said, then caught himself, realizing he had said too much. But it was too late. That single word, crooked leg in German, would lead British scientists to discover one of the Luftwaffe's most closely guarded secrets. Jones immediately began investigating. The name meant nothing initially. No intelligence reports mentioned it. No captured documents referenced it. It was as if the word didn't exist. But Jones had learned that the most valuable secrets are the ones that leave no paper trail. He began examining transcripts of intercepted German radio communications, looking for any mention of the mysterious term. On June 5, 1940, a signal intelligence unit at RAF Cheadle intercepted a transmission from a German bomber testing its equipment before a raid. The message was routine, procedural, but it contained a phrase that made Jones's pulse quicken. Beacon key Knickerbein functioning correctly, signal strength adequate for precision navigation. It wasn't a weapon, it was a navigation system. And if the Germans were testing it over Britain, that meant the beams were already operational. Jones brought his findings to Frederick Lindemann, Winston Churchill's chief scientific advisor. Lindemann was skeptical. Radio beams accurate enough for blind bombing seemed technologically implausible given the wavelengths and equipment available in 1940. But Jones was persistent. He argued that if the Germans had solved the technical challenges, if they had deployed this system without British knowledge, then every night raid would become a precision strike. London, Coventry, Birmingham, every major city could be bombed with accuracy regardless of weather, darkness, or British defences. Churchill, always attentive to technological threats, ordered an immediate investigation. On June 12, 1940, he summoned Jones to a meeting at No. 10 Downing Street. The young scientist found himself in a room with the Prime Minister, the Air Staff, and Britain's top radar experts. The scepticism was palpable. "You're telling us," Air Marshal Hugh Dowding said, his voice carrying the weight of a man who commanded fighter command, "that the Germans can guide their bombers using radio waves we cannot detect." "Not cannot detect, sir," Jones replied, his voice steady despite the scrutiny. "Have not been looking for. The wavelength would be different from our radar systems. Longer waves, lower frequency. We've been focused on our own chain-home radar. We haven't been listening for German navigational transmissions." Churchill leaned forward, his eyes sharp. "Can you find these beams, Doctor?" "Jones?" "If they exist, Prime Minister, I believe we can." "Then find them. You have 72 hours. What followed was one of the most intense scientific investigations of the war. Jones coordinated with RAF listening posts across southern England, ordering them to scan frequencies between 30 and 60 megahertz, a range they had previously ignored. For 2 days, they found nothing. Jones began to doubt himself. Perhaps Schmidt had been boasting. Perhaps the technology was still experimental. Then, on June 14th, 1940, at precisely 9:45 in the evening, a listening post near Dover detected something extraordinary. A steady, modulated radio signal at 31.5 megahertz, far stronger than any normal radio transmission. The signal formed a narrow beam, perhaps 400 meters wide, extending from the German coast directly over London. Jones was contacted immediately. The oscilloscope trace was unmistakable. 2 overlapping signals, one continuous, one in Morse dashes. When an aircraft flew along the center line where the signals overlapped, a pilot would hear a steady tone, drift to either side, and the tone would break into dots or dashes, telling the pilot to correct course. It was brilliant, it was simple, and it was already operational. The technical elegance was undeniable. The Germans had taken a commercial blind landing system, scaled it up, and weaponized it. The Lorenz system, used at civilian airports across Europe before the war, allowed aircraft to land in fog by following radio beams to the runway. The Luftwaffe had simply extended the range from 20 kilometers to 400, mounting powerful transmitters on the occupied French coast. But the true genius, from the German perspective, was the beam's narrowness. Unlike a broadcast radio that spreads in all directions, these were directed beams, focused like searchlights. The Germans believed they were undetectable unless you flew directly through them. They believed the British lacked the equipment and expertise to even search for them. They were wrong on both counts. Jones presented his findings to Churchill on June 16th. The implications were staggering. The entire Luftwaffe bomber fleet, some 1,800 aircraft, could now navigate to any target in Britain with accuracy measured in hundreds of meters, not miles. Night bombing, previously an exercise in scattering explosives randomly across the landscape, had become a precision weapon. "How accurate?" Churchill asked. "In perfect conditions," Jones explained. "A bomber following the beam could place its bombs within 250 meters of the aiming point. That's close enough to hit a factory, a rail yard, or a government building." Churchill was silent for a long moment. Then he asked the crucial question. "Can we stop them?" "Yes, Prime Minister, but not by destroying the transmitters. They're in occupied France, beyond our reach. We'll need to fight them in the electromagnetic spectrum. We need to jam the beams, bend them, make them unreliable. We need to turn their precision guidance system into a liability." Churchill's response was immediate. "Do it. Whatever resources you need, personnel, equipment, authority. Consider this a priority equal to fighter command." And so, in the summer of 1940, while the Battle of Britain raged in daylight skies, a parallel war began in the invisible realm of radio waves. A war that would save thousands of British lives and expose the fatal flaw in German technological arrogance. The British countermeasure programme, codenamed Operation Headache, began with a desperate shortage of everything. The entire British electronic warfare capability in June of 1940 consisted of Jones, a handful of engineers, and equipment scavenged from university laboratories and radio stations. The man chosen to lead the operational effort was Wing Commander Edward Addison, a former radio engineer who had joined the RAF in 1936. Addison understood that they faced 3 immediate challenges. First, they needed to map all the German beams crossing Britain. Second, they needed to design jamming equipment powerful enough to interfere with the German signals. Third, they needed to do all of this before the Luftwaffe began their nighttime campaign in earnest. They had perhaps 6 weeks. Addison assembled a team of radio operators, engineers, and pilots. They flew systematic search patterns across southern England in elderly Avro Ansons, cramped twin-engine aircraft never designed for electronic warfare. The planes were fitted with crude receivers built from commercial radio components. The operators sat hunched over oscilloscopes, watching for the telltale pattern of Knickerbein signals. By mid-July, they had mapped 3 separate beam systems converging on London, with additional beams aimed at Birmingham, Coventry, and Liverpool. Each transmitter station in France could generate multiple beams, retargeted nightly based on Luftwaffe operational plans. The Germans had created an invisible spiderweb across Britain, guiding their bombers to targets with cold precision. The mapping flights were dangerous work. The Ansons flew slowly, methodically, often at night when German beams were active. They were unarmed, vulnerable to both German fighters and British anti-aircraft guns that couldn't distinguish friend from foe in the darkness. Flight Lieutenant Balfour, who had volunteered for the first reconnaissance missions, described it as flying through a battlefield with your eyes closed, searching for ghosts. But the most dangerous work was still ahead. Finding the beams was only the first step. Disrupting them required a completely different approach. The technical challenge was formidable. The German Knickerbein transmitters were powerful, broadcasting at 50 kilowatts, equivalent to a major commercial radio station. British jammers would need to overpower these signals without alerting the Germans that their beam system had been compromised. If the Luftwaffe realized the British were jamming, they would simply change frequencies or modify their system. The solution came from Robert Cockburn, a 26-year-old engineer at the Telecommunications Research Establishment. Cockburn proposed a method called meaconing, after the old nautical term for false lights that lured ships onto rocks. Instead of crudely jamming the German beams, British transmitters would broadcast false signals on the same frequency, slightly offset from the true beam. A German pilot following what he believed was the Knickerbein beam would actually be following a subtle blend of the real signal and the British counterfeit. The effect would be gradual, almost imperceptible. The bomber's course would drift just a few degrees, not enough to trigger immediate alarm, but enough to place the aircraft miles from its intended target by the time the bombardier pressed the release switch. The genius of meaconing was its subtlety. German pilots wouldn't realize they had been deceived until their bombs exploded in empty fields instead of crowded cities. And even then, they might attribute the error to equipment malfunction or pilot error rather than British interference. But building the meaconing system required equipment Britain didn't have, and time they couldn't spare. Cockburn needed high-powered transmitters, precise frequency control, and operators who could track German beams in real time and match their modulation perfectly. He needed all of this installed and operational before the Blitz began. He had 3 weeks. The crash program to build Britain's meaconing network was a masterpiece of improvisation. Transmitters were commandeered from BBC radio stations. Antennas were erected in fields across southern England, often just miles behind the frontline coastal defences. The sites were staffed by hastily trained operators, many of them women from the Women's Auxiliary Air Force, who learned to read oscilloscopes and adjust transmitter settings with precision that would determine whether bombs fell on cities or countryside. The first meaconing station became operational on August 15, 1940, at a site near Winchester. The timing was fortunate. That very night, a force of 60 Heinkel He-111 bombers took off from bases in occupied France, their mission to destroy aircraft factories in Birmingham. Each bomber was guided by Knickerbein, following the radio beam with confidence born from dozens of successful training missions. What the German pilots didn't know was that as they crossed the English coast, British operators at Winchester began transmitting their false beam. The meaconing signal was carefully calibrated, just slightly offset from the true Knickerbein bearing. The German pilots, trusting their instruments, made minute corrections to stay on what they believed was the precise beam centerline. The navigators never noticed they were drifting south of their intended track. Their instruments showed perfect alignment. Their training had taught them to trust the technology absolutely. When they reached what their navigation equipment indicated was Birmingham, they released their bombs on schedule, on heading, by the book. The 200 tons of high explosive and incendiary bombs fell on empty countryside 15 miles south of Birmingham. Farms were cratered, sheep were killed, but not a single factory was hit, not a single war worker injured. The entire raid, planned with German precision and executed with German efficiency, had been rendered completely ineffective by British electronic deception. The German after-action reports from that night make fascinating reading. Pilots described perfect navigation, clear beam signals, and textbook execution. Yet somehow, the bombs had missed. The explanations offered were revealing: equipment malfunction, unexpected winds, map errors, pilot fatigue. Never did they consider that the beam itself had been compromised, that British scientists had penetrated their most sophisticated secret and turned it into a weapon against them. This would become the pattern for the next 6 months. German bombers, guided by what they believed were infallible electronic systems, would drop their deadly cargoes on fields, forests, and empty villages while British cities endured reduced, though still terrible, destruction. But the story of how British electronic warfare defeated Knickerbein is also a story of the men and women who operated the Meakening stations, working invisible shifts in isolated facilities, knowing that their precision meant the difference between life and death for thousands of people they would never meet. The Meakening stations were austere places. Most were Nissen huts, those corrugated metal half-cylinders that became the ubiquitous architecture of wartime Britain, placed in farmers' fields or on windswept hillsides. Inside, the temperature swung from freezing in winter to stifling in summer. The equipment generated tremendous heat, the transmitters glowing with thermionic valves that needed constant monitoring. Section Officer Dorothy Harper, a 23-year-old WAAF operator, worked the night shift at the Winchester station from August 1940 through May 1941. Her memoir, published in 1987, provides a rare glimpse into the daily reality of electronic warfare. "We knew lives depended on our precision," she wrote, "but we never saw the results of our work. We sat in that hut, watching oscilloscope screens that showed nothing but wavy green lines, adjusting dials with movements measured in millimeters. The German beam would appear on our display, and we would match it, creating our false signal just slightly offset. Too much offset, and the German pilots would notice. Too little, and the effect would be negligible. We aimed for 3 degrees of deflection. That was the sweet spot where their instruments would read normally, but their position would drift miles off course." Harper described the psychological toll of the work. "You never knew if you'd succeeded. We'd work a 6-hour shift, concentrating absolutely on maintaining perfect signal characteristics, and then go to our bunks not knowing if we'd saved lives or if our equipment had failed and bombs had fallen on sleeping families. The not knowing was the hardest part." But unknown to Harper and her colleagues, their work was being meticulously documented. RAF reconnaissance flights the morning after major raids would photograph the crater patterns, mapping where German bombs actually fell versus where they were aimed. The intelligence analysts who compiled these reports saw patterns that astounded them. A typical raid intended for the Bristol aircraft factories at Filton would see bombs scattered across a 15-mile arc south of the target. A raid aimed at the Liverpool docks would crater fields in North Wales. The Luftwaffe's vaunted precision navigation system was producing consistent errors that saved not just individual buildings, but entire neighbourhoods. Wing Commander Addison's weekly reports to the Air Ministry tracked the success rate with stark statistics. In August 1940, before Meakening was fully operational, German night raids achieved an average targeting accuracy of 800 metres from the aiming point. By September, with 5 Meakening stations operating, that accuracy had degraded to 4,000 metres. By October, with the system refined and expanded, the average error had grown to 7 miles. 7 miles. In urban warfare, That's the difference between destroying a munitions factory and bombing a residential suburb. That's the difference between crippling Britain's war production and killing sheep. But the German reaction to these failures revealed the same institutional blindness that would later plague their Enigma security. Luftwaffe intelligence officers, analyzing the pattern of bombing errors, generated increasingly elaborate explanations that never questioned the integrity of Knickerbein itself. Their first theory blamed British weather. The meteorological conditions over Britain, they reasoned, must be creating atmospheric distortion of the radio beams. This explanation seemed plausible, until raids conducted in perfect clear weather showed identical errors. The second theory involved magnetic anomalies. Perhaps Britain's geography created localized magnetic fields that interfered with compass readings, causing pilots to drift off the beam without realizing it. This theory persisted for several weeks until someone pointed out that the beam guidance system didn't use magnetic compasses. The third explanation was the most damning to German aircrew morale. Perhaps, Luftwaffe Command suggested, the pilots themselves were at fault. Navigation errors, fatigue, incompetence. This accusation infuriated experienced bomber crews, who knew they had followed procedures perfectly. The psychological impact was significant. Crews began to doubt themselves, creating tension between aircrews and command staff. Never once did German investigators seriously consider that the British had penetrated Knickerbein and were actively manipulating it. The system's mathematical elegance, its theoretical invulnerability, had become a mental barrier preventing them from seeing the obvious truth. But by late October 1940, German intelligence finally began to suspect something more sinister was happening. The evidence was becoming too consistent to ignore. Every major raid was missing its target by similar margins. The pattern was too regular to be random chance or pilot error. On October 28th, Luftwaffe Signals Intelligence issued a report that sent shockwaves through German command. Enemy activity on Knickerbein frequencies has been detected. Possibility of intentional interference cannot be excluded. Recommend immediate investigation and countermeasures. The Germans responded with characteristic thoroughness. They conducted electronic reconnaissance flights over Britain, mapping British radio transmissions. They modified Knickerbein frequencies, trying to find wavelengths the British weren't monitoring. They introduced sudden frequency changes mid-flight, hoping to break the British jamming lock. Nothing worked. The British meaconing operators, now numbering over 300 trained personnel at 12 stations across Britain, adapted to every German modification within hours. When frequencies changed, British operators found the new beams and resumed jamming. When beam characteristics were altered, British equipment matched the changes. The electronic chess match had entered a new phase. Both sides were now aware of each other, but the British held one critical advantage. They were on the defensive, reacting to German moves on their own territory with short response times. The Germans were projecting power across the channel, unable to verify whether their beams were functioning correctly, until their bombers returned with reports of missed targets. In November 1940, the Germans deployed their response. X-Gerät, a far more sophisticated beam system that used multiple intersecting beams and timing mechanisms. Where Knickerbein was elegant in its simplicity, X-Gerät was complex to the point of genius. The system worked by having the bomber fly along one main beam while crossing several perpendicular beams at precise intervals. By measuring the time between beam crossings, the bombardier could calculate ground speed and determine the exact moment to release bombs, compensating for wind drift and aircraft velocity. It was, on paper, unjammable. The British couldn't fake the timing of beam intersections. They couldn't create false perpendicular beams without knowing their precise locations and timing sequences. Reginald Jones, when he learned of X-Gerät from intercepted Luftwaffe communications, immediately recognized the threat. This wasn't just an evolution of Knickerbein. It was a completely different approach that might render meaconing ineffective. The first X-Gerät raid targeted Coventry on November 14, 1940. The Luftwaffe assembled 437 bombers, the largest night raid yet attempted. The target was the city's industrial heart, home to aircraft engine factories, machine tool works, and precision manufacturing plants critical to Britain's war effort. British intelligence, reading German communications through Ultra, knew the raid was coming. They knew Coventry was the target. What they didn't know was whether their electronic countermeasures would work against Ex-Garret. The raid was a partial German success and a harbinger of the electronic battle's future. The Pathfinder Force, elite crews using Ex-Garret, marked Coventry accurately with incendiary bombs. The main bomber stream, still using the older Knickerbein system, followed the fires and added their high explosives. The result was devastation. 568 people killed, the medieval cathedral destroyed, and significant damage to war production. But post-raid analysis revealed something crucial. The Ex-Garret Pathfinders had placed their markers accurately. However, the British had successfully jammed the Knickerbein beams, guiding the main force. Without the meaconing, the entire bomber stream of over 400 aircraft would have followed Ex-Garret markers onto the target with precision. Instead, approximately 30% of the bombs fell outside the city, deceived by jammed beams. It wasn't enough. Coventry burned, but it was proof that even against improved German technology, British electronic warfare could reduce casualties. The question was whether they could do better. Dr. Robert Cockburn returned to his laboratory at the Telecommunications Research Establishment with new urgency. Ex-Garret had to be defeated, but the timing mechanism seemed insurmountable. You couldn't fake precise time intervals between beam crossings. Unless, Cockburn realized, you changed the bomber's perception of time itself. The solution he developed was called masking. British transmitters would broadcast noise on Ex-Garret frequencies at the exact moment a German bomber crossed a timing beam. The noise would be brief, less than 2 seconds, but during that critical window, the German bombardier's stopwatch would keep running while his receiver was effectively blind. The timing discrepancy would be small, perhaps only 1 or 2 seconds, but at bomber speeds of 200 miles per hour, 2 seconds equals nearly 600 feet of horizontal distance. Multiply that error across 3 timing beams, and bombs would fall hundreds of meters from the intended point. It was a temporary solution, buying time while British scientists developed more sophisticated countermeasures, but it worked. Raids using Ex-Garret throughout December 1940 and January 1941 showed increasing inaccuracy as British masking techniques improved. The Germans responded by introducing Y-Garret, the third and most sophisticated beam system. This used a single beam with a transponder system that measured distance by radio reflection. It was simpler than Ex-Garret, harder to jam, and theoretically more accurate. But by this point, the pattern had been established. The Germans would innovate, deploy their innovation with confidence in its invulnerability, and the British would penetrate and defeat it within weeks. The cycle repeated through the spring of 1941, each German advance met by British countermeasures. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. What made the British success remarkable wasn't just technical innovation, but organizational flexibility. The German military, for all its operational excellence, was bureaucratic in its approach to technology. New systems went through lengthy development, testing, and deployment cycles. Changes to deployed systems required approval from higher authority. The British electronic warfare effort, by contrast, operated with remarkable autonomy. Cockburn and his team could design, build, test, and deploy new countermeasures in days rather than months. Operators in the field had authority to modify procedures based on real-time observations. The system was designed to learn and adapt faster than the German decision cycle. Corporal James Mitchell, an operator at the Beacon Hill Meekening Station, exemplified this flexibility. On the night of February 8, 1941, during a raid on Portsmouth, Mitchell noticed something unusual in the German beam characteristics. The modulation pattern was changing every few minutes, cycling through different frequencies in what appeared to be a deliberate attempt to break the jamming lock. Rather than waiting for instructions from headquarters, Mitchell adapted on the spot. He began manually tracking the frequency changes, adjusting his transmitter to follow the German beam through its variations. His quick thinking maintained the Meaconing effect throughout the raid, preventing the Germans from achieving the accuracy they sought. Mitchell's initiative was rewarded not with a medal, his work was too secret for public recognition, but with promotion to sergeant and a role training other operators in adaptive jamming techniques. His method was codified into standard procedures within 72 hours. This organizational agility, the ability to observe, adapt, and disseminate improvements across the entire network in days, gave Britain a decisive advantage in the electronic war. The Germans were fighting with precision and planning. The British were fighting with precision and improvisation. By spring of 1941, the Luftwaffe was facing a crisis in night bombing accuracy. Morale among bomber crews was deteriorating. Pilots, who had been assured their navigation systems were infallible, were consistently missing targets. The psychological impact was corrosive. Generaloberst Hans Jeschonek, chief of the Luftwaffe General Staff, convened an emergency conference in March 1941 to address what was now openly called the accuracy problem. The meeting brought together signals intelligence officers, operational planners, and technical experts. The conclusions reached at that conference are preserved in captured German documents now held at the National Archives. They reveal a leadership struggling to comprehend systematic failure. The final report acknowledged British interference with German beam systems but concluded, incredibly, that the interference was not technically significant and attributed continued bombing errors primarily to operational factors and crew performance. This institutional blindness would persist throughout the Blitz. Even when German engineers correctly identified British Meaconing and proposed effective countermeasures, implementation was slow and incomplete. The bureaucracy that had created such sophisticated systems couldn't adapt quickly enough when those systems were compromised. The human cost of British electronic warfare success is difficult to quantify precisely, but post-war analysis provides estimates. Professor R.V. Jones, in his memoir Most Secret War, published in 1978, calculated that Meaconing and related countermeasures caused German bombers to misplace approximately 40 to 50% of their bomb loads during the Blitz. The London Blitz alone, from September 1940 through May 1941, saw 57 consecutive nights of bombing followed by sporadic raids. Total German bombs dropped, 18,000 tons of high explosive and 17,000 tons of incendiaries. British estimates suggest that without electronic warfare countermeasures, bomb distribution would have been concentrated on strategic targets with devastating effect on war production and morale. Instead, significant percentages fell on suburbs, countryside, and non-strategic areas. This doesn't diminish the horror experienced by those who did suffer. Over 40,000 British civilians died during the Blitz, but it means that the death toll could have been catastrophically higher without the invisible shield provided by electronic warfare. The campaign of the Beam War reached its climax in May 1941 with the last major raid on London. On the night of May 10th, 505 German bombers attacked the capital, dropping 700 tons of high explosive. The raid killed 1,436 people, the highest death toll of any single night during the Blitz. But intelligence analysis of that raid revealed something remarkable. The intended target was the London docks and the industrial complexes along the Thames. However, British Meaconing had been particularly effective that night. Approximately 60% of German bombs fell outside the primary target zone, many in residential areas that, while still causing terrible casualties, represented a failure of German strategic bombing doctrine. Had those bombs fallen on their intended targets, the Port of London, already strained by months of bombing, might have been rendered unusable. Britain's ability to receive supplies from America would have been severely compromised. The war's outcome might have hung on that difference. Then, suddenly, the Blitz ended, not because of British defences or electronic warfare, but because Hitler turned east. Operation Barbarossa, the invasion of the Soviet Union, required the transfer of Luftwaffe units from the west. The strategic bombing of Britain became a secondary priority. The Beam War didn't end, but its character changed. German night raids continued sporadically through 1942 and 43, but never with the intensity or scale of the Blitz. British electronic warfare units, their skills honed and their equipment refined, achieved increasing effectiveness against each raid. By 1943, German night bombing of Britain had become almost random in its inaccuracy. A raid intended for Sheffield might scatter bombs across Yorkshire. An attack aimed at Birmingham might hit Staffordshire. The combination of British jamming, meaconing, and by then, effective night fighter defences made German night bombing operations more dangerous than productive. The institutional knowledge gained from defeating the German beams would pay dividends when the strategic situation reversed. As Bomber Command began its own night offensive against Germany, British navigators used more sophisticated versions of the same beam technology the Germans had pioneered, but they incorporated lessons learned from defeating Knickerbein, making their systems more resistant to jamming and deception. The technical expertise developed in those cramped Nissen huts across southern England by young WAAF operators watching oscilloscope traces and adjusting transmitter dials became the foundation for the entire field of electronic warfare. After the war, those techniques evolved into radar jamming, missile guidance systems, and eventually the electronic warfare capabilities that define modern military operations. But for the men and women who fought the Beam War, recognition came slowly, if at all. The work remained classified for decades. Dorothy Harper, the WAAF operator from Winchester, couldn't tell her own children what she'd done during the war until the late 1970s, when the Official Secrets Act restrictions were finally lifted. "When I could finally explain," she wrote, "my daughter asked if I'd received any medals. I told her no, we'd received something better. We'd received tomorrow. Every person who survived the Blitz because German bombs fell in empty fields instead of on their homes, they were our medal. We just never knew their names." The Beam War's legacy extends beyond the immediate tactical victories. It represented a fundamental shift in military thinking. For the first time, warfare was fought not just with visible weapons, but in the electromagnetic spectrum. The side that could dominate that invisible battlefield gained advantages that translated directly into lives saved and strategic objectives achieved. Reginald Jones, who orchestrated much of Britain's electronic warfare strategy, received proper recognition after the war. He was knighted, returned to academia, and wrote extensively about the scientific intelligence work that had been crucial to victory. In his lectures at the University of Aberdeen, where he became Professor of Natural Philosophy, he would tell students that the Beam War taught a crucial lesson about the relationship between technology and warfare. The Germans had superior technology, he would say. Their beam systems were more sophisticated than anything we had developed, but they made a fatal error. They assumed technological superiority guaranteed operational success. They never imagined that clever application of simpler technology, combined with organizational flexibility, could defeat their elegant systems. That assumption, that certainty in the face of contrary evidence, cost them the Battle of Britain as surely as if they'd lost it in the daytime skies. Flight Lieutenant Harold Balfour, who flew those early reconnaissance missions hunting for invisible beams, survived the war and lived until 1996. In an interview conducted for the Imperial War Museum in 1994, he reflected on the strange nature of the war he'd fought. "We never saw the enemy," he said. "Not directly. We saw oscilloscope traces and heard radio tones. We fought the war looking at instruments, adjusting equipment, making calculations, but the enemy was there, as real as any fighter pilot I'd fought, and when we won, when we successfully jammed or bent their beams, we saved lives we'd never see, protected people we'd never meet." It was the strangest feeling, fighting a battle where victory was invisible and defeat was measured in deaths that didn't happen. The final vindication of Britain's electronic warfare effort came from an unexpected source. After the war, Allied interrogators questioned Luftwaffe officers about the beam systems. General Major Wolfgang Martini, who had overseen much of the Luftwaffe's signals intelligence, was asked directly why the Germans had persisted with beam navigation when British countermeasures were so effective. His answer revealed the core of German institutional blindness. "We knew the British were interfering with our beams," he said, "but we never imagined they could do it so effectively. Our mathematical models showed that with our transmitter power and beam characteristics, successful jamming would require British resources we thought impossible to mobilize. We assumed they were making crude attempts that occasionally succeeded through luck. We never realized they had turned our technology against us so systematically." When shown post-war analysis of British meekening effectiveness, how consistently raids had been diverted from their targets, Martini sat in silence for several minutes. Finally, he said, "Then we were fighting a war we couldn't win. Every night our bombers took off. They were already defeated before they crossed the Channel. The tragedy is that our own confidence prevented us from seeing it." The Beam War officially ended in May 1945, with Germany's surrender. The Meekening stations were decommissioned, their equipment salvaged for other purposes. The transmitter sites returned to farmland. The Nissen huts where Britain's invisible war had been fought were torn down or converted to agricultural use. Today, few physical traces remain of the electronic battleground that stretched across southern England. A small memorial plaque at the site of the Winchester station honours the WAAF personnel who served there, though the specific nature of their work isn't detailed. The National Archives holds the operational records, declassified over decades, telling the story of one of World War II's most crucial yet least understood campaigns. The men and women who fought the Beam War mostly returned to ordinary lives. Some continued in electronic warfare during the Cold War, their expertise too valuable to lose. Others returned to civilian careers, carrying secrets they couldn't share for 30 years. They had prevented catastrophe through the invisible application of physics and courage, and their reward was the knowledge that they'd saved lives, even if they never knew exactly whose lives or how many. The story of how RAF electronic warfare defeated Luftwaffe navigation beams is ultimately a story about the limits of technological certainty. The Germans created sophisticated systems and assumed those systems were invulnerable. They couldn't imagine that the British would develop effective countermeasures so quickly or implement them so comprehensively. That failure of imagination, that certainty in the face of mounting evidence to the contrary, cost them the ability to conduct effective strategic bombing against Britain. It didn't win the war for Britain, but it prevented Britain from losing it during those desperate months when survival hung by threads. And it was accomplished not by superior technology, but by superior adaptation. By people like Dorothy Harper watching oscilloscope screens through long nights. By engineers like Robert Cockburn designing countermeasures in days that should have taken months. By operators like Corporal James Mitchell adapting procedures in real time during actual raids. By scientists like Reginald Jones who saw possibilities where others saw impossibilities. They fought a war most people never knew was happening, against an enemy that never appeared on radar or in gun sights. They fought with mathematics and electronics, with transmitters and receivers, with patience and precision. And they won. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe. February 13th, 1943. Henderson Field, Guadalcanal. The tropical heat pressed down like a weight as First Lieutenant William P. Marontate climbed into the cockpit of his F-4U-1 Corsair. The temperature hovered near 32 degrees Celsius. Sweat soaked through his flight suit before he'd even started the massive Pratt & Whitney R2800 engine. Around him, 11 other Corsairs from Marine Fighting Squadron 124 prepared for their first combat mission. The bent-wing fighters sat on the coral runway, their dark blue paint already dust-covered, their distinctive inverted gull wings casting sharp shadows in the morning sun. Marontate had trained for months on the Corsair. He knew its reputation. Carrier pilots called it the Ensign Eliminator because its long nose made landing nearly impossible. The Navy had rejected it for carrier operations, so the Marines got it instead. And now, just 24 hours after arriving at Guadalcanal, VMF 124 was about to find out if this troubled aircraft could actually fight. The mission seemed straightforward. Escort a rescue Catalina flying boat to pick up downed pilots at Sandfly Bay, Vela La Vela, 350 kilometers there and back. Standard escort work. But Marontate felt the weight of the 6 Browning machine guns mounted in his wings. 3 per side, 50 caliber, 400 rounds per gun, 2,400 rounds total. More firepower than any fighter he'd ever flown. The armament alone weighed over 500 kilograms. When all 6 guns fired simultaneously, the combined rate approached 4,800 rounds per minute, nearly 80 rounds per second. A 2-second burst put 160 armor-piercing incendiary rounds into a target. The engineering was brutal and simple. Overwhelming firepower married to a 2,000 horsepower engine. Speed, climb, and guns. The American answer to Japanese agility. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The mission went smoothly. The Catalina recovered the pilots. The Corsairs returned without incident. But the next day, February 14th, would be different. 9 PB 4Y1 Liberator bombers prepared to strike Kahili Airfield on Bougainville. 12 Corsairs from VMF 124 would escort them, along with 10 P-38 Lightnings. The combined formation departed Henderson Field at 0800 hours. They climbed to 20,000 feet, heading northwest. The Liberators droned ahead, slow and heavy. The fighters weaved above and behind, maintaining position. The flight lasted nearly 2 hours. Over Bougainville, they found their target. And waiting for them, climbing from below, were 42 Japanese A6M0 fighters. What followed became known in Marine Corps history as the St. Valentine's Day Massacre, but not for the reasons the name suggests. The Japanese interceptors rose through the bomber formation with practiced precision. The Zeros turned inside the American fighters with ease. Their pilots, veterans of campaigns from China to the Philippines to Guadalcanal, knew every advantage their aircraft possessed. At lower speeds, the Zero could outturn anything in the sky. First Lieutenant Gordon Lee Lyon Jr. dove his Corsair into a climbing Zero. He opened fire. The Zero exploded in flames, but in the chaos of the dogfight, Lyon's wingman lost sight of him. When the survivors returned to Henderson Field 2 hours later, Lyon was missing. So was another Corsair pilot. 8 total American aircraft were destroyed, including those 2 Corsairs. The pilot, Flight Petty Officer 2nd Class Yoshio Yoshida, had collided with Lyon's Corsair during the engagement. Both men died. The after-action reports were sobering. American pilots claimed 14 Japanese aircraft destroyed. The actual number was 1. The Japanese claimed 17 fighters and 5 bombers. The actual losses were 8 fighters and 1 bomber. Everyone overclaimed. But the fundamental truth was undeniable. The Corsair's first major engagement had been a disaster. The bent-wing bird that the Navy had rejected, that Marines had reluctantly accepted, had just lost 2 aircraft without achieving meaningful results. And across the channel in Rabaul, Japanese commanders received the intelligence reports with satisfaction. The Americans had deployed a new fighter. It was fast, heavily armed, but apparently no more effective than the Wildcats and P-42s they'd been defeating for over a year. Commander Takeo Shibata, intelligence officer for the Japanese Naval Air Force at Rabaul, reviewed the combat reports. The new American fighter, designated F-4U, showed high speed in level flight and diving attacks, but it turned poorly. Its pilots seemed inexperienced. Most critically, it appeared vulnerable to the standard Zero tactics that had proven successful since December 1941. Climb above, dive through, break away. The Zero's superior maneuverability at low speeds remained decisive. Shibata's conclusion appeared in multiple Japanese command briefings. The F-4U represented no fundamental threat. It was another American attempt to compensate for pilot skill with engine power and heavy armament. Impressive on paper, manageable in practice. This assessment would prove catastrophically wrong, but in February 1943, the evidence supported Japanese confidence. They controlled the skies from Rabaul. Their pilots were experienced. Their Zero fighters had dominated Pacific combat for over a year. One more American fighter type would not change the strategic balance. What the Japanese did not understand, what they could not see from combat reports and wreckage analysis, was that the Corsair represented something more fundamental than a new weapons system. It embodied a completely different philosophy of air combat. A philosophy built not on individual pilot skill or aircraft agility, but on systematic advantage, overwhelming firepower, and industrial replacement. The Americans were not trying to build a better dogfighter. They were trying to build a weapon system that made dogfighting obsolete. The story of this transformation begins not at Henderson Field in February 1943, but 3 years earlier, in the design offices of Chance Vought Aircraft Corporation in Stratford, Connecticut. February 1940. Chief designer Rex Beisel faced an impossible specification from the United States Navy. The requirement document demanded a single-engine fighter capable of at least 400 miles per hour in level flight. That speed exceeded anything then operational in the world. The British Spitfire topped out at 360 miles per hour. The German Bf 109 reached 350. The Japanese Navy's newest fighter, not yet encountered in combat, could manage 330. 400 miles per hour required unprecedented power. Beisel selected the largest radial engine available, the Pratt & Whitney R2800 Double Wasp, 18 cylinders arranged in 2 rows, 2,000 horsepower. The engine alone weighed over 1,000 kilograms. To accommodate the massive 13-foot diameter propeller needed to absorb that power, Beisel designed an inverted gull wing. The wing center section angled sharply downward from the fuselage, then bent upward to the wingtips. This configuration kept the landing gear short while maintaining propeller ground clearance. The design was unconventional, distinctive, unmistakable, but it worked. The first XF-4U-1 prototype flew on May 29, 1940. Test pilot Lyman Bullard pushed the aircraft to 405 miles per hour in level flight, the first American fighter to exceed 400 miles per hour. The Navy ordered production immediately, but Beisel's design philosophy extended beyond pure performance. He specified 6 50-caliber M2 Browning machine guns, 3 mounted in each wing panel, outboard of the wing fold. Standard American fighters carried 4 guns. Some carried 6, but typically with less ammunition. The Corsair carried 400 rounds per gun, 2,400 rounds total. The Browning AN M2 aircraft machine gun fired at approximately 800 rounds per minute. 6 guns generated a combined rate of 4,800 rounds per minute. That firepower density meant a 2-second burst delivered 160 rounds. Each 50-caliber projectile weighed 43 grams. Armor-piercing incendiary rounds could penetrate 13 millimeters of steel at 500 meters. They could ignite fuel tanks. They could destroy engine blocks. They could cut through airframe structures. This was not precision shooting. This was area saturation. Point the nose, press the trigger, overwhelm the target with volume. Where Japanese designers had optimized for pilot skill and aircraft maneuverability, American designers optimized for pilot survival and target destruction. The difference was philosophical. Japanese doctrine emphasized the warrior, American doctrine emphasized the weapon system. By July 1942, the first production F-4U-1 Corsairs rolled off the Vought assembly line. By December, VMF 124 began receiving aircraft for training, but the Corsair had problems, serious problems. The long nose blocked forward visibility during landing approach. Pilots couldn't see the carrier deck until the final seconds. The powerful engine generated torque that twisted the aircraft during takeoff and landing. The stall characteristics were unpredictable. The left wing tended to drop without warning. At the Navy's carrier qualification trials in September 1942, the Corsair failed, too dangerous for carrier operations. The decision devastated Vought engineers. The aircraft they'd designed specifically for carrier operations couldn't operate from carriers. But the Marine Corps needed fighters desperately, and Marine squadrons operated from land bases. Henderson Field on Guadalcanal, fighter strips in the Russell Islands, forward operating bases throughout the Solomons. The Corsair's carrier deficiencies didn't matter if it never landed on a carrier, so the Navy gave the Corsair to the Marines, and in February 1943, VMF 124 brought it to combat. That first engagement over Bougainville on February 14th seemed to confirm every criticism. 2 aircraft lost, minimal results. The Corsair appeared to be another American failure. The Marine pilots filed detailed after-action reports. They noted the Zero's superior turning ability. They described how Japanese pilots could reverse inside the Corsair's turning radius, gaining position for deflection shots. They documented the difficulty of maintaining formation during high-speed combat. The reports reached Major General Ralph Mitchell, commander of Marine Aircraft Wings Pacific. Mitchell had seen this pattern before: new aircraft, inexperienced tactics, predictable losses. The solution wasn't different aircraft. The solution was different doctrine. The Corsair couldn't outturn the Zero. Fine, don't try. The Corsair was faster than the Zero. Use that. The Corsair could outdive the Zero. Use that. The Corsair was more heavily armed and armoured than the Zero. Use that. Mitchell's staff drafted new tactical guidance. Never dogfight. Never slow down. Never try to match Japanese manoeuvrability. Instead, maintain altitude advantage. Dive through enemy formations. Fire short, concentrated bursts. Extend away at high speed. Climb back to altitude. Repeat. The tactics emphasized team coordination over individual combat. 2 Corsair sections would work together. One section would bait Japanese fighters into turning engagements. The other section would dive from above, attacking while the Zeros maneuvered. It was methodical, scientific, impersonal. Everything traditional fighter combat was not. And many Marine pilots resisted it initially. They'd grown up on stories of World War I aces, circling dogfights, individual duels, the romance of aerial combat. Mitchell's doctrine stripped away that romance. It demanded discipline over instinct, system over skill. But it worked. By March 1943, after 2 months of refined tactics and additional training, Corsair squadrons began achieving positive kill ratios. VMF 124 claimed 5 Japanese aircraft on April 1st with no losses. VMF 213, the second Corsair squadron to reach combat, shot down 8 Zeros on April 7th for the loss of 1 Corsair. The aircraft hadn't changed. The pilots had barely changed. The tactics had changed everything, and Japanese commanders were beginning to notice, but they still didn't understand what they were facing. From their perspective, American fighter performance was improving, but this was expected. New pilots gained experience. Losses generated learned lessons. It was the natural progression of warfare. What they failed to recognize was that American doctrine had fundamentally shifted. The United States was no longer trying to defeat Japanese fighters in individual combat. They were trying to create conditions where individual combat never occurred. Speed, altitude, firepower, position, these became the decisive factors, not turning radius, not pilot skill, not aircraft agility. The Corsair was designed around this philosophy from the beginning. 2,000 horsepower, 400 miles per hour, 6 guns, 2,400 rounds, armor plate behind the pilot, self-sealing fuel tanks. The aircraft could absorb damage that would destroy a Zero and still bring its pilot home. And when the Americans lost a Corsair, they built another, and another, and another. Vaught's Stratford plant, Goodyear's Akron plant, Brewster's Philadelphia plant. 3 companies, multiple production lines. By mid-1943, Corsairs were rolling off assembly lines at a rate of 300 per month. Japan's entire fighter production across all types was approximately 500 per month, and their production was decreasing as the war consumed resources and destroyed factories. American production was increasing. In August 1943, a new Marine squadron deployed to the South Pacific, VMF 214. On paper, it was a reconstituted unit. The original VMF 214 had completed their combat tour and returned stateside for rest and reassignment. But Major Gregory Boyington, a former Flying Tigers pilot with 6 victories in China, convinced his superiors to let him rebuild the squadron with a hand-picked group of pilots. Most were replacements from other units. Some were considered difficult. Some had disciplinary issues. Boyington didn't care about their records. He cared about their willingness to fly his way. Aggressive, fast, unrelenting. They called themselves the Black Sheep. 27 pilots, 27 Corsairs, deployed to Munda on New Georgia Island in September 1943. From there, they could reach Japanese bases throughout the Northern Solomons, and they could reach Rabaul. That changed everything. Rabaul sat at the northern tip of New Britain Island, 640 kilometers northwest of Guadalcanal. The Japanese had captured it from Australian forces in January 1942. By mid-1943, it had become their primary fortress in the South Pacific. 5 airfields ringed Simpson Harbour, Lakunai and Vunakanau, pre-war Australian strips, Rapopo, completed in December 1942 with concrete runways. Tobera, finished in August 1943, and Keravat on the north coast. Combined, these airfields had capacity for over 400 aircraft. 367 anti-aircraft guns defended the approaches. The harbour itself could accommodate dozens of ships. Submarines operated from underground pens carved into the volcanic rock, storage facilities, repair shops, barracks for over 100,000 troops. Rabaul was more than a base. It was a fortress city. The Japanese called it the Gibraltar of the Pacific. For 19 months, it had been effectively untouchable. Allied bombers from Port Moresby, 500 miles distant, could barely reach it. When they did, Japanese fighters rose to meet them. Zeros dominated those engagements. But in September 1943, American forces captured Vella La Vella in the Central Solomons. Marine engineers carved an airstrip from jungle. Suddenly, Rabaul was within range. Not bomber range, fighter range. For the first time in the war, American single-engine fighters could reach the Japanese stronghold, fight over the target, and return with fuel reserves. The strategic equation had fundamentally changed, and the Marines were ready to exploit it. September 16, 1943, VMF 214's third mission. 24 Marine Corsairs escorted Navy dive bombers to Balali Island at the southern tip of Bougainville. The formation climbed to 24,000 feet. Japanese radar detected them 70 miles out. Zeros scrambled from Kahili Airfield. 50 enemy fighters rose to intercept. Boyington led the Black Sheep into the formation. The Japanese pilots attempted their standard tactics: climb above, then dive through with superior turning ability. But the Corsairs didn't turn. Boyington's section dove straight through the Zero formation at over 400 miles per hour, too fast for the Zeros to track. As they extended away, the second section dove from above, catching the Zeros while they were still turning to pursue. First Lieutenant Robert McClurg found a Zero in his gun sight at 300 yards. He pressed the trigger. All 6 guns fired simultaneously. The combined muzzle flash lit up his cockpit. The Zero disintegrated, not caught fire, not went down. Smoking, disintegrated, pieces of wings, fuselage, engine cowling scattered across the sky. The engagement lasted 11 minutes, 20 Japanese aircraft destroyed, no American losses. The mission established VMF 214's reputation, but more importantly, It validated the tactical doctrine. Speed and firepower defeated maneuverability, system defeated skill. The pattern repeated throughout September and October. Corsair squadrons flew increasingly aggressive missions into Japanese-controlled airspace. The losses flipped. By October 1943, American fighters were achieving kill ratios of 6-1, sometimes 10-1 against Japanese aircraft. And then, on December 17th, the first American fighter swept directly over Rabaul itself. Boyington led 48 Marine Corsairs from Torokina Airfield on Bougainville. They crossed the 130 miles of open water over St. George's Channel. At 0900 hours, they arrived over Simpson Harbour at 20,000 feet. Below them, Japanese shipping filled the harbour. Around them, the volcanic peaks of New Britain rose through tropical clouds. And climbing to meet them, 60 Japanese fighters, Zeros, the latest models, piloted by veterans. This was supposed to be a massacre, Japanese defensive fighters operating over their own base, against American attackers at the extreme limit of their combat radius. Every advantage favoured the defenders, except one. The Corsairs had more firepower than the Japanese had ever encountered from single-engine fighters. The engagement developed exactly as American doctrine prescribed. The Corsairs maintained altitude. When Zeros climbed to engage, the Marines dove through at high speed, 6 50-caliber guns per aircraft, 48 aircraft, 288 guns total. When multiple Corsairs targeted a single Zero, that Zero simply ceased to exist. The volume of fire was unprecedented. A Zero attempting evasive maneuvers faced not individual aimed shots, but walls of tracers. Armor-piercing incendiary rounds punched through the Zero's unprotected fuel tanks. The aircraft's legendary lack of armor, the design choice that gave it superior range and maneuverability, now meant instant death. One 2-second burst from a single Corsair was often sufficient. 50 rounds, 2,100 grams of projectiles, travelling at 2,800 feet per second. The kinetic energy was devastating. Boyington himself shot down 4 Zeros that morning. His wingman got 3. Across the formation, Corsair pilots methodically destroyed Japanese fighters. When fuel ran low after 90 minutes over target, the Marines turned south. They landed at Torokina with minimal damage. Behind them, 30 Japanese fighters burned in the jungle or floated in Simpson Harbour. Japanese commanders were stunned. Rabaul had never been penetrated like this. Never. The fortress that had stood impregnable for 19 months had just been violated by American, carrier-rejected fighters operating from a coral strip on a barely secured island. Commander Shibata's intelligence assessment changed overnight. The F-4U was not just another American fighter, it represented a fundamental threat. The after-action analysis revealed the truth. The Corsair's 650 caliber guns, firing simultaneously, delivered approximately 4,800 rounds per minute combined. That translated to 80 rounds per second, 240 rounds in a 3-second burst. Each gun carried 400 rounds. At full trigger, a Corsair could sustain fire for approximately 30 seconds before ammunition exhaustion. But no pilot fired continuously. Controlled bursts, 2 seconds, 3 seconds, maximum efficiency. And even with that discipline, the firepower overwhelmed Japanese aircraft. The Zero, designed for agility, had no answer to volume fire. You cannot outmaneuver 80 projectiles per second. You cannot evade what you cannot predict. The mathematics were simple and brutal. More guns, more ammunition, more destructive capacity per aircraft, multiplied by formation tactics that maximized concentrated fire. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The raids continued through December and January. VMF 214 flew mission after mission over Rabaul. Other Marine squadrons joined them. VMF 222, VMF 223, VMF 321. Corsairs became a daily presence over Simpson Harbour. The Japanese sent up interceptors. Veterans from carrier air groups. The best pilots remaining in the Navy Air Service, they died anyway. On December 23rd, Boyington led another sweep. His score stood at 24 victories, just 2 short of Eddie Rickenbacker's World War I record of 26. On December 27th, he shot down number 25. The engagement occurred at 12,000 feet over Rabaul. Boyington dove on a 0, making a climbing turn. He opened fire at 400 yards, closed to 200. The 0 exploded. Pieces of the aircraft tumbled past his canopy. He claimed another kill minutes later, but that one wasn't confirmed by witnesses. Still, 25 official victories, 1 short of the record. On January 3rd, 1944, Boyington led 70 Corsairs on a massive sweep over Rabaul. He engaged a 0 at high altitude, 2-second burst. The 0 caught fire, his 26th victory, tying Rickenbacker's record. But in the chaos of the engagement, Boyington's Corsair was hit by return fire. He ditched in St. George's Channel. His wingman, Captain George Ashman, went down nearby. Both men survived the crash. A Japanese submarine recovered them. Boyington spent the next 20 months as a prisoner of war. He survived, Ashman did not. The Black Sheep Squadron completed their second combat tour 3 days later. In 84 days of combat operations, they had shot down 94 Japanese aircraft. They had destroyed another 97 on the ground. 8 pilots became aces. The squadron's kill ratio was 11-1, but the numbers only told part of the story. The real story was what happened to Japanese air power at Rabaul. Between December 17, 1943, and February 19, 1944, American fighters flew continuous raids against the fortress. The intensity was unprecedented. Daily strikes, sometimes multiple missions per day, Marine Corsairs, Navy Hellcats, Army P-38 Lightnings. But the Corsairs bore the brunt of the fighter sweeps. Their firepower, their speed, their systematic tactics devastated Japanese air groups. Japanese records documented the losses. From November 1943 through March 1944, approximately 359 Japanese aircraft were destroyed defending Rabaul. That number included fighters, bombers, reconnaissance aircraft. It included veterans with hundreds of combat hours and rookies with barely 50. It included aircraft from frontline carrier air groups rushed to Rabaul to reinforce the defense. Those carrier groups, the elite units of the combined fleet, lost 50% of their fighters, 85% of their dive bombers, 90% of their torpedo bombers. In 10 weeks of combat over Rabaul, the Japanese Navy lost the equivalent of their entire carrier air capability, not to American carriers. To land-based fighters operating from forward strips, the strategic implications were catastrophic. When American forces struck the Gilbert Islands in November 1943, Japanese carrier aircraft couldn't effectively oppose them. They'd been destroyed at Rabaul. When American forces invaded the Marshall Islands in January 1944, Japanese naval aviation could barely respond. The pilots were dead. The aircraft were gone. Lieutenant Commander Tadashi Nakajima, a Zero pilot who survived the Siding-Baker Rabaul campaign, wrote in his post-war memoir, "We understood that American production exceeded ours. We understood their pilots were becoming more experienced. What we did not understand until Rabaul was that they had fundamentally changed how fighter aircraft fought. The Corsair did not try to be a better Zero. It tried to make the Zero irrelevant, and it succeeded." But perhaps the most telling assessment came from Japan's greatest surviving ace. Saburo Sakai, credited with at least 28 victories, wrote in his autobiography Samurai that the Corsair was the most feared of all Allied aircraft. Not the fastest, not the most maneuverable, the most feared. Because Japanese pilots understood what facing a Corsair meant. If it caught you, you died. The armor-piercing incendiary ammunition would ignite your fuel tanks. The volume of fire would shred your airframe. The speed differential meant you couldn't escape. Your only chance was to avoid engagement entirely. That was the ultimate irony. The Zero, designed as the ultimate dogfighter, now survived only by refusing to fight. By February 1944, Japanese commanders at Rabaul issued new instructions to surviving fighter pilots. Do not engage corsairs in combat unless absolutely necessary. Avoid head-on passes. Avoid diving attacks. Maintain altitude advantage if possible, but do not dive through American formations. The instructions contradicted everything Japanese fighter doctrine but necessity overrode doctrine. The alternative was death. On February 19, 1944, the final major air battle over Rabaul occurred. American fighters found minimal opposition. Most Japanese aircraft had been withdrawn. The survivors pulled back to Truk, then to the Philippines. Rabaul, the Gibraltar of the Pacific, was neutralized, not captured, not destroyed, neutralized. 100,000 Japanese troops remained garrisoned there. The airfield still functioned. The harbour could still accommodate shipping. But it no longer mattered strategically. Allied fighters controlled the airspace. Allied bombers cratered the runways at will. The fortress had become a prison, and the Corsair had been the primary weapon of that transformation. By war's end, United States production of F-4U Corsairs exceeded 12,000 aircraft. Vought built 4,700. Goodyear built 4,100. Brewster built 735. The squadrons flew 64,000 combat sorties. They claimed 2,140 aerial victories against 189 losses, an 11-to-1 kill ratio, the lowest loss rate of any fighter in the Pacific War. Against the Zero specifically, the ratio was 12-to-1. Against Japan's later, more advanced fighters like the Kawanishi N, 1KJ, George, the ratio was 6-to-1, still overwhelming. The Corsair dropped 15,621 tons of bombs, 70% of all bombs dropped by American fighters in the Pacific. It destroyed countless ground targets, ships, airfields, supply depots, infantry positions. The bent-wing bird that the Navy had rejected became the most effective multi-role fighter of the Pacific War, and it achieved that success not through superiority in traditional fighter characteristics, but through a fundamental reimagining of what fighter combat should be. The captured Japanese intelligence documents told a story that American analysts initially dismissed as propaganda. Reports from surviving Zero pilots describing their encounters with Corsairs. The language was consistent across dozens of accounts. Overwhelming firepower, impossible to evade. Our maneuverability meant nothing. Technical Sergeant Harold Fukuda, a Japanese-American translator working for Marine Intelligence, compiled these reports in March 1944. His analysis noted a pattern. Japanese pilots weren't complaining about American skill. They weren't attributing losses to better tactics, though those certainly existed. They were describing a fundamental mismatch in weapons philosophy. One report, from a pilot identified only as Flight Warrant Officer Hayashi, stationed at Rabaul in January 1944, was particularly stark. We were taught that air combat is decided by pilot skill and aircraft performance. The Americans have proven this wrong. Their Corsairs do not need superior performance in turning. They do not engage us on our terms. Instead, they impose their terms through speed and firepower. When 6 machine guns concentrate on your aircraft for 2 seconds, no amount of skill saves you. No evasive maneuver works. You simply die. This was not the complaint of a defeated warrior. It was the observation of a professional, recognizing that the rules had changed. The Japanese had built an air force around individual excellence. The Americans had built an air force around systematic advantage. Both approaches worked, but only one scaled. Only one could sustain losses and continue fighting. Only one could be taught to replacement pilots in months rather than years. The Zero required 18 months to train a fully qualified combat pilot. The Corsair required 6 months of flight school plus 2 months of tactical training. The difference wasn't in aircraft difficulty. Both were challenging to fly. The difference was in combat philosophy. A Zero pilot needed to master aerobatic maneuvering, deflection shooting, energy management in turning fights, skills that required hundreds of hours to develop. A Corsair pilot needed to master formation flying, diving attacks, gunnery at high speed, skills that could be systematically taught and reinforced. When Japan lost experienced pilots, they lost years of accumulated expertise. When America lost experienced pilots, they lost men. Tragic, grievous, but replaceable. The industrial equation reinforced this asymmetry. By 1944, the United States was producing fighters at 10 times Japan's rate. Pilot training throughput exceeded Japan's by even wider margins, and the aircraft themselves embodied different values. Consider the weight breakdown. An F4U-1 Corsair weighed 4,175 kilograms empty. An A6M50 weighed 1,876 kilograms. The Corsair was more than twice as heavy, but that weight wasn't dead mass. It was armor plate, self-sealing fuel tanks, stronger airframe structures, more powerful engine, heavier armament. Each kilogram served pilot survival and mission effectiveness. The Zero's lightness bought range and agility, but it bought them at the cost of protection. A Zero pilot flying over Rabaul in January 1944 knew that a single burst from a Corsair meant death. Not probable death, certain death. The psychological impact was devastating. Warrant Officer Kuniyoshi Tanaka, shot down over Rabaul on January 27, 1944, and recovered by Japanese naval forces, described the experience. "I saw 3 Corsairs diving toward our formation. I thought I could evade. I'd evaded American fighters before, P-42s, Wildcats. But these were different. The volume of fire was impossible. I rolled left. Tracers followed. I reversed right. More tracers. I pushed the nose down. The tracers converged. My wing exploded. I don't remember ejecting. I woke up in the water with my aircraft burning around me." Tanaka survived. Most didn't. The kill ratio told the story, but the ratio only measured aircraft destroyed. It didn't measure missions aborted because Japanese fighters refused engagement. It didn't measure the psychological toll of flying against an opponent whose firepower made survival random. By March 1944, Japanese fighter units at Rabaul had been withdrawn. The remaining pilots were reassigned to homeland defense. New pilots, with minimal training, arrived to replace them. These replacements lasted for days, sometimes hours. First Lieutenant Robert Hansen of VMF 215, flying Corsairs over Rabaul in January 1944, noted the change. "The quality of Japanese pilots has declined dramatically. We're seeing aircraft that fly in straight lines, that don't attempt evasive maneuvers. I shot down 3 in one mission, and none of them tried to escape. They just kept flying straight while I closed from behind. It felt wrong, like target practice, not combat." Hansen accumulated 25 victories in 17 days of combat. He died on February 3, 1944, when his Corsair was hit by anti-aircraft fire over Rabaul. He was 23 years old. He received the Medal of Honor posthumously. His brief, intense combat career illustrated both the effectiveness of Corsair tactics and the unforgiving nature of Pacific air combat. But his observations about Japanese pilot quality were accurate. Japan's training pipeline had collapsed under attrition. The experienced pilots who had opened the war, men with thousands of flight hours, were dead, killed over Rabaul, over the Solomons, over New Guinea. Their replacements had 50 to 100 flight hours, barely enough to take off and land safely. Against Corsairs flown by Marines with 200 to 300 hours, these rookies stood no chance. The mathematics were simple: superior aircraft, superior firepower, superior tactics, superior training infrastructure, superior industrial capacity. Japan had none of these advantages by mid-1944. What they had was courage, discipline, a willingness to die for the emperor. These were not trivial qualities, but they were insufficient against a war machine built on systematic advantage. The American way of war didn't ask for individual sacrifice. It asked for professional competence in a system designed to maximize effectiveness while minimizing risk. The Corsair embodied this philosophy. Armor protected the pilot. Self-sealing tanks prevented fires. The massive engine could absorb battle damage and continue running. Multiple hydraulic systems provided redundancy. The airframe could sustain combat damage that would destroy lighter aircraft. Corsairs returned from missions with dozens of bullet holes, damaged control surfaces, failed systems. They landed safely. The pilots walked away. The aircraft were repaired and flew again. This was unthinkable in Japanese doctrine. Aircraft were expendable. Pilots were expendable. The mission was everything. The Corsair said the pilot was valuable, worth protecting, worth bringing home. That philosophical difference defined the Pacific Air War's outcome. By August 1945, the Japanese Navy had virtually no combat-capable carrier aircraft remaining. The Army Air Force was reduced to kamikaze attacks because conventional combat was no longer viable. The pilots who might have challenged American air superiority were dead, killed at Rabaul, killed over the Philippines, killed defending the homeland. Meanwhile, American fighter strength continued growing. Corsairs, Hellcats, Mustangs, Thunderbolts, thousands of aircraft, tens of thousands of trained pilots, an industrial and training capacity that Japan could never match. The bent-wing bird that Japanese commanders had laughed at in February 1943 had become the symbol of their aerial defeat. Not because it was the best fighter aircraft ever built, not because it was invincible, but because it represented a system that worked, a philosophy of war that valued the warrior enough to protect him. That trusted in firepower over finesse. That understood air combat was won through systematic advantage, not individual duels. The final statistics were comprehensive. From February 1943 through August 1945, Corsair squadrons flew 64,051 operational sorties. They claimed 2,140 air combat victories. They lost 189 aircraft to enemy fighters. The overall kill ratio exceeded 11-1, but these numbers obscure the human cost. 189 Corsairs lost to Japanese aircraft meant approximately 150 American pilots killed or captured. Each one a trained professional, each one mourned by family and squadron mates, each one a life ended in violent combat. The Japanese losses were proportionally worse. 2,140 aircraft destroyed meant approximately 2,000 Japanese pilots killed. Most of them burned alive when 50-caliber incendiary rounds ignited their unprotected fuel tanks. Some survived to be captured. Most didn't. The Pacific offered few opportunities for successful bailouts. The ocean swallowed the wreckage and the dead without distinction. Among those dead were some of Japan's finest aviators, men who had opened the war with attacks on Pearl Harbor and the Philippines, who had dominated early Pacific combat, who had believed in their aircraft and their training. They died because their commanders had built an air force optimized for one kind of war, and the Americans fought a different kind. This single aircraft, the F-4U Corsair, provided irrefutable evidence of the fatal miscalculation. Japanese commanders who laughed at early combat reports in February 1943 were silent by February 1944. The bent-wing bird they'd dismissed had systematically destroyed Japanese air power throughout the South Pacific, had neutralized Rabaul, had achieved kill ratios that made conventional air combat suicidal for Japanese pilots, had proven that firepower and systematic tactics defeated individual skill and aircraft agility. The lesson transcended aviation. It spoke to fundamental approaches to warfare. The Japanese built a military around warrior ethos, individual excellence, spiritual strength, acceptance of death. The Americans built a military around industrial capacity, systematic training, technological advantage, protection of personnel. Both systems produced brave men willing to fight and die, but only one system was designed to win a long war of attrition. The Corsair story is not just about aircraft. It's about what nations value, what they're willing to sacrifice, what they're willing to protect. The Japanese valued the mission above the man, the aircraft as expendable as the pilot, range and agility over armor and survivability. The Americans valued different things. They built aircraft to bring pilots home. They designed tactics to minimize losses while maximizing effectiveness. They created training systems that could replace casualties. They harnessed industrial capacity to overwhelm opponents through sheer material advantage. History rendered its verdict in the wreckage of Japanese air power. In the neutralized fortress of Rabaul, in the kill ratios that averaged 11-1. In the survival of American pilots who walked away from damaged aircraft. In the deaths of Japanese pilots who had no such option. By war's end, the commanders who had laughed at the Corsair in 1943 were either dead or facing defeat. The aircraft they'd dismissed as another American failure had become the most effective fighter bomber in the Pacific, and the Marines who flew it had proven that systematic advantage, properly exploited, defeats individual excellence every time. The bent-wing bird flew on. Corsairs served in the Korean War. They flew ground support missions until 1953. Some remained in service with foreign air forces into the 1960s. The last combat mission was flown in 1969 by the Honduran Air Force, 26 years after that disastrous first engagement over Bougainville. A quarter-century of proving that the Japanese commanders who laughed were catastrophically wrong, and that the Americans who trusted in firepower, armor, and systematic tactics had understood the future of air combat better than anyone realized in February 1943. When Japanese engineers examined captured Corsairs after the war, they found the same things that Corsair pilots had known all along: thick armor plate, self-sealing fuel tanks, robust structure, 6 heavy machine guns. The aircraft weighed twice what a Zero weighed. But every kilogram served a purpose: protection, firepower, survivability, the philosophy written in aluminum and steel. Value the pilot, bring him home, let him fight again tomorrow. That philosophy won the air war over the Pacific. Not the best aircraft, not the bravest pilots. The philosophy that understood modern war required sustainable systems, not individual heroes. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.